So I'm going to be traveling for the next month. So which means that most of the lectures for the next month will be on Zoom. If it's not going to be on Zoom, I'll let you know. But by default, you're going to assume that it's on Zoom. And the Zoom link is the one that's on the course website, cmumlsp.github.io, right? So just to let you know. All right. In the next couple of lectures, so today we're going to begin talking about independent component analysis, but I won't actually be talking about independent component analysis. We will be going over some of the basics. And the actual ICA lecture will be next Tuesday, which should work. So let me start by asking you guys a question, right? So let me ask Adrian. Let's say I have a tube, right? And I only have white balls and black balls. Okay. And my friend is on the other side of this wall. I have a tube from here to there. And I flip a coin. And I want to let him know if I got a heads or a tails. How would I do it?
Assign heads or tails to.
I have a tube. I have black, white, but I can roll balls through it. I have white balls and black balls. What would I do? So black would be for heads. White would be for tails. I just roll a ball through, right? Pardon me?
Could be the other way around as well.
Doesn't matter, but we're going to choose some kind of a standard and say, if you get a black ball, it's heads. If you get a white ball, it's a tails. So how many balls am I rolling per outcome? Just one, right? So this is easy, no big deal. Now, so have you guys seen four-sided dice? They're like this, they're long, they have four sides, and if you roll it, it's going to be one of those four sides. So now let's say I still have the same tube, I still have a collection of balls, I roll a four-sided die. And I want to tell my friend the outcome. How would I do it? Two balls, right? So I'd send them maybe two black balls for one, a black and a white for two, a white and a black for three, two whites for four, right? So again, so how many balls do I send per outcome? Two. Okay. Let's say I have an 8-sided octahedral die. So the outcomes are going to be between 1 and 8. How many balls am I going to send per outcome? 3, okay. I have a regular 6-sided die. How many balls am I going to send per outcome? 3, because that's all. I need at least, if there are 6 distinct outcomes, I need at least 3 balls, right? Or can I do better? Any ideas? Yes. Okay, keep talking. That doesn't change anything, right? So there are 6 outcomes. So you're going to have. So we can work that out. It's not going to improve on what we just got. So how would you improve on this? Yes, Timian.
Yeah, we could still add somewhat like a square, like a power of 2. So
power of 2 meaning?
So many, and the number of outcomes in total is around like a power of 2.
So you're saying you can batch it, right? So what I can do is send, instead of sending individual rolls, I can send the dice twice, roll the dice twice. How many different outcomes do I have? If I roll the dice twice? 36, right? So then how many balls would I need to send for to let my friend know what the pair of outcomes was? 6, right? 2 raised to 5 is 32. 2 raised to 6 is 64. I still need 6. So how many balls per dice? Still 3. So I have not really improved matters a bit. Now suppose, but let's, maybe we're on something, right? We're still 3 bits per row. So maybe if I can go on to grouping 3 of these things. And so I roll the dice 3 times and I send the triple to my friend. So if I send the triple, how many distinct combinations of triples do I have? 6 raised to 3, 216, right? How many dice, how many balls will I need to send? 8 to send out a triple. 8, right? So how many balls per outcome? That's 8 divided by 3, right? That's 2.666. So this seems to be helping, right? Maybe we're getting better. So what would the next thing to do be?
Another roll.
Add another roll. I can do this 4 times, right? So, but if I batch 4 rolls, there are 1,296 combinations. And that means 11 bits per outcome, right? 2.75 bits per roll. So the number actually increased. But then if I batch 5, there are 7,776 combinations, 13 bits per outcome, 5 rolls, 2.6 bits per roll. Right. So as I keep batching things, this is the size of the batch. 1, 2, 3, 4, 5, 6, and so on. If I was sending individual outcomes, it was 3, right? If I was sending pairs, it became something like 2.66. Then 3, it went up a bit to 2.75. Then 4, it went down to 2.6, right? For 5, oh no, 4, wait, for 2, what was it for 2? 2 was still 3, right? 2 was still 3, then it went down here, then it went down here, it went down to 2.6. If I keep increasing this, where will this all end? If I begin batching infinite of them together, where will that end? Around log 2 of 6. Why do you think so?
Because it is sort of the optimal.
Can you be here a little more rigorous about it? Why would you think so? Anybody? Yes, Lucy.
Yeah.
Can you speak up, please? Yeah.
Oh, I have to guess, you have the intersection between and 6 to the.
So here's what you're going to get, right? There are 6 raised to n outcomes if I'm batching n of those. If I take a log, there are log 6 raised to n, log base 2, right? If I'm sending it in bits. So n times log base to the 6. But then am I actually sending n times log base 2 of 6? No, that's not an integer, right? So what would I actually be sending? The ceiling. Correct? That's how many bits I'm sending. Make sense? So per roll, that's going to be divided by n. Correct? And so if I look at this error, right? If I look at n log base 2 of 6, or log base 2 of 6 minus ceiling, actually, let me put it this way, minus ceiling n log base 2 of 6 divided by 6. What is the upper limit on this? What is the cap on this? One? So this is good. The difference between this is going to be 1, right? Because when you take a ceiling, it's 1 at most, right? And so when I divide by n, that's simply going to be 1 over n, right? And so, make sense, Lucy? when you round something up, what is the largest amount you're going to increase it by? 1. So the difference between the ceiling and the floating point value is at most 1. Divide by n for rolls per outcome. So this is going to be less than or equal to 1 over n. Limit n tending to infinity, what does this become? 0. So if you actually keep going ahead, where will this end? This is actually going to end at log base 2 of 6. Which is why when somebody asks you, how many bits do I need to represent k outcomes? You might say log base 2 of k, but is that true? Meaning if I have to represent 7 outcomes, can I really send log of 7 bits? No, so what are we really speaking of? Ceiling, no. So see, the ceiling is not log base 2 of 6, right? When I'm saying that it takes log of n, where n is the number of outcomes, it means that when I batch infinite of these together, then the average number of bits per outcome is log of n. So anytime we speak of these things, we are always speaking of batches that are infinitely large. You're not really speaking of individual outcomes. It's something you have to speak of, right? When we speak of communication in general, we're always speaking of what happens in the limit. Does that make sense to everybody? Right? So, moving on. Questions? None? All right. Here's a point. Okay, what's the answer to the first one? The second? Beautiful, right? Everybody got this. Okay. But now, a 4-sided dice needs 2 bits per roll. But then you find that not all sides are equally likely, right? So maybe you get 1, it's a loaded dice. You get 1 half the time. You get 2 and 3, 2 a quarter of the time. And 3 and 4 each occur 1/8 of the time, right? In this case, can you do better than 2 bits per outcome? Can you do better than 2 bits per outcome? How would you do this? Again, think of this. I'm sending balls down the pipe to my friend. And my friend has to receive the balls and he has to know exactly what the outcome was. So how would I do this? Anyone? Isaiah knows the answer. Of course you do. Everybody knows. Diana knows the answer. She knows everything. Okay, yeah, give me an encoding, right? What can I do? Go ahead. Your turn. Tell me how I could deal with this.
The less common ones, like the more common ones means less.
Okay, you are giving me a general principle. Give me a solution, right? Can somebody give me a solution? Hamid, you know everything. Okay, can someone give me a solution to this? Vidar.
For the first one.
Okay, if I get 1, I send a 0, okay?
Then 1, 0.
So that's for 2, I send a 1, 0.
Then 1, 1, 0.
Then I send a 1, 1, 0.
And then 1, 1, 1.
And then a 1, 1, 1. So what happens now? Would this work? Would this work? Okay. Why would this work?
Because whenever I receive a zero, it's termination.
So whenever I receive a zero, it's terminated. So look at this. So how frequently am I going to be sending zero? Half the time, right? So it's 1 bit half the time, right? How frequently am I sending a 1 0? Quarter of the times, right? So 2 times 1/4. And then how frequently am I sending a 1 1 0? 1/8 of the time. So three bits 1/8 of the time, and these 3 bits are also 1/8 of the time, right? So what is the number of bits I'm sending per outcome on average? 1 times half plus 2 times 1/4 plus 3 times 1/8 plus 3 times 1/8, right? That's going to be half plus 6/8, which is 3/4, which is 1.75 bits. Did that arithmetic make sense to you guys? Right. And so I'm actually sending fewer than 2 bits per outcome because what did we exploit?
Distribution.
That not all outcomes are equally probable, right? And so now to go back and address Vidur's suggestion, can I do this instead? Can I send a 0 for 1, a 0 1 for 2, a 0 0 1 for 3, and 1 1 1 for 4? Would this be acceptable?
Yeah.
No, right? Because it's confusable. If I got a 0 0 1, I don't know if it's two rows or 1. This could either be a 3 or this could be a 1 followed by a 2. You don't really know. Whereas this one is unambiguous. Every time you get this, you know exactly, if I get a 0, then the sequence of bits until the 0 tells me the number, unless I get 3 1s, in which case I know it's a 4, right? So there's something magical over here. So this works, right? The receiver is never in any doubt as to what they received and what is the average number of bits per outcome. If you work it out, that comes to 1.75. But then let me ask Vidur again. How did you know this?
I think I've done similar thing with the interview.
You've done similar, okay. Besides, memory, right? Why did you think you could get away with just 1 bit for 1 and you needed 2 bits for 2? And why did you think it was possible to come up with a scheme, an unambiguous scheme, which allowed you to do this? Any ideas? Yeah.
0.5 is the same as like from coin being encoded.
Fantastic, right? So here's what it is. If I just had a long sequence of trials, infinite trials, right? What fraction of these trials is going to be 4? 1/4 of those guys, correct? And so you're going to have some subset of these, which are 1/4. Now, from the perspective of the 4, it's occurring 1/4 of the time, right? Each individual occurrence of 4 thinks it's one of 4 equally likely outcomes. From the perspective of 4, how many alternatives do you choose 4 from? 8, right? You might as well have been rolling an 8-sided dice from the perspective of 4, because the probability of 4 was it's occurring 1/8 of the time, correct? That makes sense? Yeah.
Why can't I just use 0 0 0 1 1 0 1 1? Would be equal to 1.5 in that case.
What?
I can say if it was 1, I can do 0 0.
Uh-huh.
It is 1 0.
Uh-huh.
3, it is 0 1. And for 4, it's 1 1. Would that give me like P is equal to 1.5 instead of 1.7?
Would it give me 1.5?
So.
If you send it, right? Let me send you. It's going to be. Can somebody tell me why this doesn't work? It doesn't work. Mhm.
This is not 1.5, this is 2.
I'm sending 2 bits, right? It's not 1.5, right? Okay.
If you do like 0 for 1, 1 for 2, and like the same pattern for the other,
0 for 1, 1 for 2,
the 1 for 0 and 1.
and then 1, 1, 0. How do you know that this is not 2 2's followed by 1? This is ambiguous, correct? So the only unambiguous way is, what we do proposed, or you can flip the ones and zeros, okay? So that's a Huffman code. But then here's the point. 4 occurs 1/8 of the time. From the perspective of 4, it's the outcome of an 8-sided dice, right? So let's say I'm sending a very large number, n outcomes, then what is the expected number of 4s that I'm sending? N over n times 1/8, right? On each occasion, as far as 4 is concerned, I'm rolling a 8-sided dice. How many bits would I be sending? 3, right? And so this is how many bits you're going to be sending, using to send the 4s, right? And how many bits to code each instance of 4? When 4 is the outcome of the rules of an 8-sided dice, it's 3. So the number of bits I need to send 4s in my large sequence is n over 8 times 3, right? So that's basically what I'm expected showing over here. So the average per occurrence of 4, what is it? Per occurrence of 4. Just be dividing by n, right? Over here. So average per row. Now let's move on. Let's consider another one. If I consider the number 1, what fraction of the outcomes is 1? 1/2, right? So every second one is going to be a half. And exactly how many, from the perspective of 1, what was it the outcome of? It was a flip of a coin, right? So from the local perspective of 1, you might as well have been flipping a coin. So how many bits to encode each instance of 1? There are n over 2 times 1, right? So if I look at the total across all of the outcomes, it's n times p of 1 times log of p of 1, right? Or log of 1. Is it log of p of 1? It's log of 1 over p of 1, correct? Why? Okay. So if I have the probability is 1 over 8, it's like saying there are 8 possible outcomes. So 1 divided by the p of 1, right? Plus n times p of 2 times log of 1 over p of 2, and so on. This is how many bits we needed to send the entire sequence, right? How many bits per outcome? Divide by n. Which is going to be summation I pi log 1 over p of I. Right? If you've ever wondered where that formula came from, you can sort of work your way through it. It's fairly straightforward. How many of you remember seeing this formula? The famous formula for entropy, right? So this is how it comes across. So what is the entropy of a random variable really telling you? It's not telling you how random it is. What it's really telling you is if I had infinite outcomes, if I was sending infinite outcomes, draws of this random variable, using an optimal mechanism for encoding the outcomes, not any other thing. If I used an optimal mechanism for encoding the outcomes, and I sent an infinite of these outcomes, then on average, per outcome, This is how many bits you would be sending. That makes sense? Right? It's the average number of bits per outcome when you batch infinite of them together under an optimal coding scheme. There's no other coding scheme that you can think of which will give you a better a lower number of bits per outcome. Okay. And this is also known as the entropy of the random variable. Questions? Okay. And so, in general, an outcome X is probability P of X. From the perspective of P of X, how many sided dice is it an outcome of? It has to be 1 over P of X, right? And how many bits to code an instance of X? It's going to be n times P of X times log of 1 over P of X. So expected number of bits per outcome for any outcome is going to be just n times, P of X times log of 1 over P of X. You average this over all the outcomes, you end up with the formula, right? So that gives us the famous formula for entropy. Now, here, that's where this number came from. I know that from 0, the fact that the 0 occurs half the time means that there is an encoding scheme where I only have to send 1 bit per outcome, right? The fact that 1 occurs a quarter of the time means that there's an encoding scheme where I only have to send 2 bits per outcome. The fact that 3 occurs 1/8 of the time means there's an encoding scheme where I only have to send 3 bits per outcome. But is this always going to be true? What we are really saying is I'm going to send 3 bits per outcome on average, not per outcome, right? It just so happens that in this particular example, it's very convenient. It also happens to be the per outcome value. But if I was sending a long stream of messages, eventually it's going to come out to approximately this much, very close to this much, using an optimal scheme. Make sense? Okay. So the average number of bits per symbol required to communicate a random variable over a digital channel using an optimal code is this term, summation pi log of 1 over pi. Pi is the fraction of times it happens, and log of 1 over pi is the optimal number of bits per occurrence when you transmit infinite of those. And this must be summed over all of the outcomes, right? You cannot do better. There is no other coding scheme that is going to require fewer bits per outcome. This is the best you can do. And so this is the entropy of the random variable. Questions? Okay. Okay, Johnny, for the first statement true. Or second one. Okay. So the entropy of the distribution is not the number of bits needed to transmit the outcome of a single draw. It's the average number of bits needed to transmit an outcome when we batch infinite outcomes together using an optimal coding scheme. Okay? So that's what entropy means. So now that we have the basic notion of entropy, we'll just do a very, very brief review of basic information theory. If I have a random variable, x, then there's a then the entropy, generally represented as h of x, is the number of bits that you're going to need on average to send an outcome, right? It's the minimum average number of bits required to transmit a symbol. It's not just under any odd scheme. It's the absolute minimum that you can send and still have the receiver unambiguously decode what was said, what they've received. So if I've got, if you got this pipe and there are people walking into my room and I want to tell my friend on the other side If the people walking in are tall or of medium height or they're short, then it's going to be, this is a random variable with 3 outcomes, right? And so the number of balls I'd be sending per person coming in on average using the optimal coding scheme would be the entropy of that random variable. Now, you can also have a joint entropy of multiple random variables. So what is the joint entropy of random variables? Suppose I want to convey to my friend, not just their height, but also their gender, right? So now this looks like 2 different random variables. One is the height and one is the gender. So if I just wanted to convey the height, how many bits would I need to send on average per outcome? Anybody?
2.
Mm-hmm. 2? No. It's going to be h of x, whatever the distribution is. I didn't tell you, right? So it's going to be the entropy of the distribution of heights. Come on, guys, wake up, right? So if I just wanted to convey the information about the gender of the person who came in, how many bits would I need to send on average?
It should be a distribution of
The entropy of the distribution of the gender, right? So this is good. But then, so each person coming in has a height and a gender. If all I'm sending is the height, then I'm going to send the minimum number of bits is the entropy of the height, right? If all I'm sending in is the gender, the entropy I'm going to send in is the entropy of the gender. So when people come in, and if I'm conveying this information to my friend in the other room, am I going to be sending one set of balls about the height and another set of balls about the gender without considering the relationship between the two? Not necessarily. Why? Because if I look at the combination of height and gender, how many combinations will I have? I have tall, medium, and short, male and female in my example, right? How many combinations do I have? 6. So how many outcomes is the random variable really defined over? 6 possible outcomes, right? And so if I were looking at this, that is going to be the joint entropy of H. So this is over 6 outcomes. This is over 3 outcomes. This is over 2 outcomes, right? So what can you tell me just intuitively? If I were sending information about both height and gender jointly, would I be using the same number of bits as if I sent information about height and then sent information about gender separately? Not likely. Why not?
because the new number of bits on average would be the entropy of the joint distribution.
Because gender informs about height, right? Women are more likely to be on the shorter side. Men are more likely to be on the taller side. And so if you look at this distribution, this is not simply going to be P of H comma G. It's not going to be simply P of H, P of G. If the height and gender didn't really interact, then you could be sending information about height and information about gender. You don't have to worry about how they interact. But more realistically, they do interact. And so what you're going to find is H of X comma Y is less than or equal to H of X plus H of Y. Very simple, right? It's very easy for you to figure out why this must be the case. Okay, so now let me talk about something called conditional entropy, right? So you guys with me so far? But now suppose, so this is what you get if I have one pipe for height, another pipe for gender. And here, if I'm just sending height, I'm bundling height and gender together and sending it through a fat pipe. Okay. But now suppose, just suppose that I have this gender pipe and it's free. So think of transmitting bits. I'm sending bits to my friend. And every time I roll a ball down this pipe, I pay some money. I pay a cent. Anytime I send money, send something through this pipe, I don't pay anything. Okay. I still want to convey information about the people's height of the person walking into the room to my friend. Can I use this setup to save money?
Yes.
How?
Because the two variables are not independent, that means you can save bits likely by sending a free like gender.
Go ahead. How would I do this?
You would just take the conditional distribution of like your height given your gender and use the entropy of that, how many bits you can send on average.
Yes, go ahead.
You can assume basically if it's a male initially that the guy is gonna be tall unless you state otherwise through the height thing.
So here is what I can do, right? I can send the height through this guy. If I send the height through this guy or the gender through this tube. And so I first inform my friend, the person who just came in as male, and it doesn't cost me anything to convey this information, right? So then the entropy I would have to consider is the probability of height given male, correct? And this is not simply going to be the distribution of heights in general. Males are more likely to be tall than short. And so now if I use the optimal coding for P of H given M, I'm going to be using fewer bits than if I simply use P of H, right? Similarly, if I informed the person who just came in is female, then I'm going to be using P of H given F, right? So under this condition, how many bits would I be sending on average to inform my friend about the heights?
Should be a conditional distribution.
What is that going to be? What is that going to be? I'm assuming you guys are with me so far, right? So what is this going to be?
The sum of the probability of each height given whatever gender, like times the negative log of that same probability.
You're giving me a formula, but here, anytime the person is male, I'm going to be giving h of height given male, right? That is the entropy, that is the number of bits I'm going to be sending on average for every male person that came into the room. What is this going to be? This is going to be summation over heights, P of height given male, log of 1 over P of height given male, right? Everybody with me? Every time the person was female, what would I have? The entropy of height given female, correct? So, but then I've segregated the males and the females out. On average, how many bits am I going to be sending per outcome? This is what I'm going to be sending per outcome when the person's male. This is what I'm going to be sending per outcome when the person is female, right? So on average, how much would I be sending per outcome?
What's the probability of the person being male and female?
Pardon me?
What's the probability of the
So that's going to be the probability of male times h of height given male plus probability of female times h of height given female, correct? This is what you'd be doing on average per outcome across all possible outcomes. Make sense? And this, of course, is this of course is this guy over here. And so if I write the formula out, tell me if I begin to lose you. None of this is particularly complicated, once you begin thinking about tubes and tall people and short people and men and women. So that's going to be summation over gender, probability of gender, times summation over height, right? Probability of height given gender, log of 1 over probability of height given gender. Everybody with me? Which is simply going to be the summation over height and gender, P of H comma G, log of 1 over P of H given G. This is just what the arithmetic works out to be. Yeah, we just said tall, medium, and short, right? Doesn't really matter if it's discrete or not, but when you get to continuous variables, things get a little more quirky. The same logic still holds, right? So do you see how this whole thing works out? Okay, now tell me this. So are you guys with me so far? Now, if I have an extra pipe through which I can send the gender for free, am I going to be spending more money or less money than if I didn't have the pipe? Should be less, right? So what can you tell me about this relationship between, this is the conditional entropy of height given gender. Observe that this is different from H of H given M. There I'm looking at a specific value for gender. This is the conditional entropy of height given gender. Okay, so what can you tell me about the relationship of the conditional entropy of height given gender to the conditional entropy of height? It's going to be less than or equal to, right? So conditional entropy of height given gender is going to be less than or equal to the entropy of height. Everyone with me so far? Perfect, okay. So what's the difference between the two? Right, okay. So again, we're always speaking of, you missed all the fun stuff. Okay, everybody agrees with me on this, right? If everybody agrees with me on this, then what is H of height minus H of height given gender? Look at the picture of the pipes again. Actually, sorry, this was going to be I've got something. No, I'm missing something here. So the other thing I want to talk about is, now suppose I want to compute, send both height and gender, right? Then will I be spending more money or less money than if gender went for free? I'm going to be spending more, right? So this is going to be greater than or equal to H of H given G. So what is the difference between the two? If I wanted to send both height and gender, right, and it costs me money, I'm allowed to do anything, any which way, right? So H of H comma G is how much money I'd be spending using an optimal coding scheme for height and gender, right? H of the entropy of H given G is how much money I'm going to be spending if gender went for free.
So this is the entropy of gender.
This is just going to be how much money I'd be spending to send the gender, right? So this is optimal. That's the optimal stuff that that's the lowest amount I'm going to spend on sending gender. But once I send the gender, the other guy's got the gender, so I can send the height, right? And so this is in general, you're going to get H of X comma Y is going to be H of X plus H of Y given X. Simple logic, right? If you think of everything in terms of tubes and pipes and balls, it begins to make sense. You don't have to work your way through the arithmetic, right? Questions? Okay. So this is the conditional entropy and yeah. All right. So I'm going to move on. We'll come back to entropy in a bit. I just wanted to introduce the basic notions of entropy and conditional entropy and such like. And we wanted to introduce the notion of independence in that joint. What is P of X given Y if X doesn't depend on Y? What is H of X given Y if X doesn't depend on Y? So let's say people's heights don't depend on gender. Am I going to gain anything by sending gender on the pipe? No. So what is h of the entropy of height given gender? It's just going to be the entropy of h. So when I have two variables which are independent, then the conditional entropy is just going to be the entropy of the local variable. The joint entropy is going to be the sum of the low individual entropies. Whatever it costs me to send the gender, whatever it costs me to send the height, right? So again, principles that we will be using in independent component analysis. So the next thing we're going to look at is correlation versus the statistical concept of correlations. Two variables x and y are correlated if knowing x tells you something about the expected value of y. And they are uncorrelated if knowing x tells you nothing about the expected value of y, although it could give you other information. So what do I mean by this expected value of y? First, what is correlation, right? Correlation doesn't mean causation. Now, this is a well-known fact that the consumption of burgers has gone steadily up over the past couple of decades. The consumption, the penguin population of Antarctica has steadily gone down over the past couple of decades. How many of you think that this means we're eating penguins? Right? There is no, one is not causing the other, right? They just happen to be, there's some other common cause, maybe, but they're just statistically correlated, right? And so, unless of course McDonald's has a top secret Antarctica division for harvesting penguins, right? Now, if I were to plot this time, if I draw burgers versus penguins, penguin consumption, sorry, burger consumption versus penguin population, you're going to get plots like this. One is going up with time, the other is coming up with down with time, right? And so at each time I have a penguin and burger combination. If I plot the scatter, it's going to look like this. When the burger consumption is low, the penguin population is high, and vice versa. Now, if you saw the scatter, just looking at the scatter might give you the completely erroneous impression that we're eating penguins, but we're not, right? So now, here, they are correlated in the sense that variations in one imply variations of the other. It doesn't mean they cause variations of the other. It means they imply variations of the other. And so, two random variables, x and y, are uncorrelated if and only if the average value of the product of the variables equals the product of their average values. Expected value of x times y is the expected value of x times the expected value of y, right? But what this really means, this is a very fancy way of saying that the average value of y does not depend on x. So here's this picture again. This is the penguin population versus burger consumption. If I told you that the burger consumption is B1, and I ask you, what is your estimate for the penguin population in Antarctica? You're going to give me a number that you read off the line, right? Then if I tell you that in this particular year, I'm not telling you what the year is, the burger consumption was B2. What do you think the penguin population was in Antarctica? You're going to come up with a second number, which is B2, which you're going to read off the line. So penguin populations are anti-correlated, but they're correlated, right, to burger consumption. Now, on the other hand, if the two were not correlated, then you'd get a scatter of this kind. So the burger consumption is B1, your estimate for how many penguins are in Antarctica is going to be the same as when the burger consumption is B2. So these are uncorrelated random variables, right? So knowing x does not tell you what the average value of y is. Again, it's about the average value. We're not talking about the variance, right? If you look at all the different years in which the burger consumption was B1, the actual scatter might have some spread, but the average value is the same across all the years. And now when this happens, knowing x doesn't tell you anything about the expected value of y, but then you can flip the page around, and knowing y doesn't tell you anything about the average value of x either. The average value of y is always the same regardless of x. The average value of x is always the same regardless of y. X and y are uncorrelated. Okay. So here are some probability distributions. the first two of them are Gaussian, the third is a cylindrical kind of Gaussian distribution, the other is a square. In the top left, do you think X and Y are correlated? The distribution to the top left. The figures, the line figures are showing the equal probability loci. So X and Y are not correlated, right? Because if you look at this over here, if I have a probability distribution that looks like this, then the mean across all x's, the mean, the mean of y is always the same across all x's. So x and y are uncorrelated. What about to the top right? Are they correlated or uncorrelated? To the top right. So over here, look, here's what the distribution looks like. This is what the distribution looks like. So if I told you x is this value, what is the average value of y? It's going to be somewhere here. If I told you x was here, what's the average value of y? It's going to be somewhere here. So is the expected value of y a function of x?
Yes.
So are they correlated or uncorrelated? All right, what about to the bottom left? Are x and y correlated or uncorrelated? Uncorrelated also. Bottom right? Also uncorrelated, right? Knowing x, the middle of the distribution of y doesn't depend on x, okay? So that's the notion of correlatedness. Uncorrelatedness of variables is generally considered desirable when you're modeling data, both modeling and analysis. If you're doing any kind of modeling based on Euclidean error, which we did all over the place when we were computing pseudo inverses, when we were computing all kinds of things, we were using Euclidean error. And in this case, if your variables are uncorrelated, you can handle them independently. So because the value of one doesn't affect the average value of the other. Otherwise, you have to consider the interactions and things get very annoying. So often when you have correlated random variables, we will try to uncorrelate them, decorrelate them, right? We'll try to transform them to something where the correlation has gone to zero. So let's say I have this penguin versus burger consumption. These are two variables, x and y. Then I want to transform my variables such that the distribution now becomes axis aligned. Here the distribution is at an angle. I want to make it axis aligned. And then what does this require me to do? It requires me to rotate the distribution or transform the space. Either way, I'm going to put this through a linear transform M such that so if this is x and y, I want to convert them to x prime, y prime, so that the distributions are axis aligned, right? Makes sense to everybody? So I'm going to assume that the data are zero mean for now. So what does uncorrelated mean? You have some expected value of x prime, some expected value of y prime. These are the transformed variables, right? And so you want the expected value of y prime to not depend on x prime after you've rotated the space, meaning at every point, the average value of y is the same. So also you want which also means that the expected value of the product of x prime and y prime is always simply going to be the product of the expected values of x prime and y prime, right? And if the data are all zero mean, all of these terms will be zero. Now that's all fine, but let's look at what the correlation matrix for the transformed variable is. Again, go back here, right? X prime, y prime is my transformed variable. That's this guy. XY is this guy, right? I am transforming XY through some matrix M. That's my linear transformation. And so if I look at the correlation matrix, assuming it's zero mean for now, that's simply the expected value of the vector times its transpose. We saw this in the previous classes, right? The correlation matrix is going to be just the vector. You multiply it by its transpose, it's going to become a full matrix, a square matrix. You average this over many, many examples. That's your expected value of the outer product. That's your correlation matrix. It's going to be, the expected value of x prime squared, x prime, y prime, x prime, and y prime squared. And so moving the expectation in, which you can, this is the expected value of x prime square and the expected value of y prime square. Now, if x and y are uncorrelated, I'm assuming zero mean for now, not, I can always make things zero mean by subtracting the mean out. Then I want these diagonal terms to be zero. Right. So that's when, so I know that x prime and y prime are uncorrelated if the diagonal terms of my correlation matrices are zero. And so if I just take, if I call each of these vectors something y, these guys, some y, so then I can have a large matrix of these vectors, right? And what would this would mean that y times y transpose is zero. So if I look at the math, here's what I would get. Let me get, I'm sort of using this block X. In the original space, I had a bunch of data points, right? And each of these is a vector. So let me put all of these into a big matrix. And this is my block X. Then after transforming it, that's going to be some other bunch of vectors. So these I can put into a big matrix, Y. So Y1, Y2, and so on. I'll call this the block matrix Y. And so based on our transformation, we know that Y equals M times X, right? So the correlation matrix is going to be proportional to Y times Y transpose, which is simply going to be M times X transpose times M transpose to within a scaling constant. If I take the X, so, but then X times X transpose is simply the covariance matrix of X, correlation matrix of X, and you want this guy to be diagonal, right? So this actually tells me this is what I've got. Let's say I just consider this one. This is the correlation matrix of my centered X. If I perform eigen decomposition of it, then I can always write this as some E times the eigenvalues times E transpose. Again, we saw this in class, right? And so what we really want is M times, so we want this guy to be diagonal. We want M times XX transpose M to be diagonal, which is to say M times the covariance of X times M transpose to be diagonal. But then the covariance of X can be written as M times, this is the eigenvectors of this covariance matrix, times lambda times E transpose times M transpose to be diagonal. Right. So how would this work? If M times E were an identity matrix, then E transpose times M transpose is also going to be an identity matrix. And then you're left with the diagonal matrix lambda, which just tells me that I just want my, or is it M? So maybe I'm sort of mixing things up a bit, but basically what you're going to find is that if you just take the eigenvectors of your covariance matrix as your transform, the transposition of the eigenvectors of your covariance matrix as your transform, that's going to rotate the space so that the variables are uncorrelated. Now, I'm not going to go into the math. I'll confuse myself. You'll confuse yourselves. Just look at the slide, but you get the idea. Where this comes from is that if you actually perform the eigen decomposition of the covariance matrix, the matrix of eigenvectors, when transposed, is going to represent the set of axes that for the uncorrelated, decorrelated data. So basically what happens is if your data look like this, then the eigenvectors for your for the covariance matrix are going to be these two guys. And so when you transform the space by the transpose of the eigenvectors, this is going to become the new x-axis. This is going to become the new y-axis, and now your data are going to be decorrelated. Right? It diagonalizes the covariance matrix. Again, so far so good. So this is what principal component analysis does. Principal component analysis we saw is combining the eigenvectors of the covariance matrix. So it's going to be finding the coordinates of each data point on these guys. And thereby, these guys now become the new axes. And the data points become points in this space where the axes are now, the data are now axis aligned. So this is, that's what PCA does, okay? It diagonalizes the covariance matrix, but let's move on, right? So here is a bunch of data. Without getting into the math, right? Here's a bunch of data. I'm finding you, are the data uncorrelated? Are X and Y uncorrelated? Over here. Yes or no? Yes, okay. But is there another pair of axes where it's also uncorrelated? These two guys, right? So the set of axes that can decorrelate your data is not unique. Two different things, right? Now, how about this? Are the data on X and Y uncorrelated? Yes or no?
Yes.
Is there another pair of axes where they're also uncorrelated? No? Here's the thing. You made an assumption when I said this, when you said this. What's your answer? 180 degrees is still going to be the same thing, right? If they're not at 90 degrees, if you get rid of the idea that your bases must be orthogonal to one another, then I can find you other bases which also decorrelate the data. This actually ends up being very important, right? So when we did non-negative matrix factorization, our bases were not at 90 degrees. In fact, they were guaranteed not to be at 90 degrees, pretty much, except in the extreme case. So once you get rid of this notion that the bases must be orthogonal to one another, then you're going to decorrelate the data as well. So yeah. All right. Wait, first one.
False.
All right. Second one. True. Third. All right. Right. So there are many different sets of orthogonal bases along which the components are decorrelated, and the rest, of course, gobbledygook. Okay. So that's correlatedness. But then let's go on to this notion of independence and dependence. Two variables, X and Y, are dependent if knowing X gives you any information about Y. And they're independent if knowing X tells you nothing about Y. Okay? So probabilistically, if you want to write math, the joint probability of two variables, X and Y, is going to be the product of the individual probability distributions if X and Y do not inform about one another, right? And so independence implies uncorrelatedness. Uncorrelatedness doesn't imply independence. If the two are independent, then knowing X doesn't tell me anything about Y, let alone its average value, right? On the other hand, knowing the average value doesn't mean that not knowing anything about the average value doesn't mean I don't know anything. So let's see some examples. Two independent variables. So, but before that, so here are other ways of quantifying it. How do I know that two variables X and Y are independent? Even before this, let me see if I can get to my pictures, right? Yeah. Look at this guy. Top left figure, are X and Y independent? Because Y is Gaussian, and Y is the same Gaussian at every value of X. Okay, top right, are X and Y independent? Yes or no? They're correlated. If they're correlated, they cannot be independent, right? Bottom left, are X and Y independent? Are they independent? Yes? Okay. So here is, the probability distribution is a hard cylinder, correct? So from the top, the distribution always looks like this. Does knowing X tell me anything about Y? Knowing X doesn't tell me the average value of Y. But if I know that X is here, I know that Y lies only in this range. Right? If I know that X is here, I know that Y can lie in this range. Make sense? So knowing X doesn't tell me anything about the average value of Y, but it does tell me something about Y. It changes the bounds of Y. So now are X and Y independent here? Yes, no, 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 no. Johnny, you look confused? Okay, so here's the thing. Suppose I told you that the probability distribution of X and Y was this. X and Y always lie inside this circle, but it's uniform within the circle. Okay, suppose I told you X is this. What can you tell me about Y? It lies only within this region, right? Suppose I told you X was out here. What can you tell me about Y? It can lie entirely anywhere within this entire region. So are X and Y independent? No, right? But are they correlated? They're not correlated because the average value of Y is always the same at every value of X. But knowing X tells me something about Y. Right? That makes sense? Okay. So how can I convert? So we know how to decorrelate things. And what is the notion of uncorrelatedness? The notion of uncorrelatedness was this, that expected value of xy was the expected value of x times the expected value of y. This was our notion of uncorrelatedness, correct? The notion of independence is not uncorrelatedness. So how can I convert independence to uncorrelatedness? Here's how I do it. The thing is, give me any two functions f and x. I don't care what the functions are. Give me any two functions f and x. And if the expected value of f of x times g of y is the expected value of f of x times the expected value of g of y, for every pair of functions f and g, this means x and y are independent. What this means is that if I can manipulate x, and this has no influence on y, and if I can manipulate y, and this has no influence on x, regardless of how I manipulate x and y, then the two are independent. That makes sense? So let me give you an example to see. So for example, if I had my distribution of this kind, right? So in this case, if I compute if I square every x, for instance, right? This is a bad example. Gaussians are horrible things, but I can come up with other examples. But this is going to hold. For any f and g, I can manipulate the x and y independently. If I can do that, they're independent. I'll try to come up with a better example. Okay? So there's another thing that comes out, which means that these are properties that we will hold, that we will use in the next class. That if I have some random variable whose probability distribution is symmetric around the mean, say around 0, and if I transform the random variable through a function of this kind, then the expected value of the transformed random variable is going to be 0. Because for every x, there's a minus x, and f of x has the same probability as minus f of x, right? And so they will cancel each other. So anytime, if your function is odd symmetric, its expected value is 0. This is something, again, this is a generic property of probability distributions. So here are all the various, some of the other things that we saw when we were looking at in the infotheoretic principles. So how are we going to use all of this, and why is any of this relevant? Yeah.
So because slide spread, you show like different functions, like the previous one. So like so in the last part, like last year, what about they are like uncorrelated, but what about the independence?
The last one, they are independent, because when you go off the edges, their probability is 0. Anywhere where you have a non-zero probability of x, Knowing X doesn't tell me anything about Y. Right? Yeah. So, okay, so far so good, right? Now let's try to go back and link to things. Here, we saw earlier, if I gave you some music and I gave you some notes, you can you can project the music onto the notes, you can determine the scores. Similar, the problem was what are the scores given the music, and we did this using the pseudo inverse. We also went the other way. I could give you the scores and I could ask you the notes, and you could use the same pseudo inverse mechanism to find the notes, right? No big deal. But then when we spoke of principal component analysis of the Carr-Hannon-Love transform, as we saw it, the real question we were asking is, I give you neither the notes nor the score. I'm just telling you that this entire music was composed of only 4 notes. What are my notes? And then you ended up coming up with the notes, right? Did we actually find the notes when we did this? Here's what we find, right? So this was the least square solution, and that gave us PCA. But going back, what PCA will do, again, I'm going to skip the math because we have 10 minutes left, is when we perform PCA of the original data, our notes were orthogonal, our bases were orthogonal, right? So this has a very interesting consequence, the modulations. So if all the columns of W are orthogonal to one another, it's very trivial to show that the rows of H are also orthogonal to one another. It will just happen, okay? So I'll skip all of that. So let's see how that works. Let's go back to principal component analysis. And in PCA, I just told you that, here's this music. Find me the notes, right? So here's a piece of music, and this one actually has only 12 notes. I'm going to play. Okay, and now I'm going to try to find the notes in the music, and using the techniques that we just saw, I could just use principal component analysis on this, and I'm going to get a bunch of bases. And if our decomposition technique was just right, then the bases we found would be the individual notes. So let's see if that really works. Here's the first note I found. Does this sound like a pure note? Okay. Stop. What about this one? Not really. It's very mixed, right? Again, this is not a pure note. It sounds somewhat like a pure note, but it doesn't like a note, but it's all got all kinds of things mixed in it. So why is that? Why did we not actually get notes? There's an implicit assumption that when we perform PCA, that the modulations of the individual notes are uncorrelated. So it tells me that the rows of H do not inform about one another. That's a part of the decomposition of principal component analysis. Then why this is the case? Take a look at the slides. The math is fairly trivial. I just don't want to do this on the board. Okay. So when I do this, basically you're just saying that if I take my H matrix and multiply it by its own transpose, the result is going to be a diagonal matrix. So you're saying that there is no correlation between how I play one note and how I play the other note. Clearly, this is not a very meaningful constraint to be imposing implicitly or explicitly on your decomposition, which is why we're going to get rubbish decompositions. Okay. But then, so one last poll. Okay, Hanan, give me the answers. So decorrelation is not sufficient to determine semantically meaningful bases. We did see that non-negativity, was that sufficient? Not necessarily, right? You might actually have negative components in your data. It worked out only when you had compositionality as part of the constructive process for the data. In the generic case, you can make no such assumption, right? So is there any other constraint that we can look for when we are trying to decompose our data? So here's another one. I can assume that the score for one node is not merely uncorrelated with the scores for the other node. I can assume that the score for one node is completely statistically independent of the score for the other node. So which is like saying that I've got one person playing my first note using any odd how, and I have another person playing another note any odd how, and these two guys don't hear one another, they aren't talking to one another, but somehow the music was formed. Now, this is a very crappy assumption to be making, but it turns out that it actually does a good job in many situations. And so in this case, we'd be assuming that the instruments are playing independently of one another. It's not strictly true, but then, we can still try. And this is what we're going to see in the next class. What would happen if in principal component analysis, the constraint that we imposed was that the scores for the nodes were uncorrelated. The average value for any note did not depend on how much any other note was being played at any time. Now, instead of just the average value, we're going to take one step further and we're going to say the distribution of any note doesn't depend on the distribution of any other note. Those scores are independent. And this business of trying to find statistically independent components of the mixed signal is what we call independent component analysis. We'll see this in the next class. So for principal component analysis, this is what we really had. Notes and score, W times H. We were trying to find the W and H, which minimize the square error between the original data and WH. But for principal component analysis, we had a second constraint, which said that the bases B must be orthogonal to an orthogonal matrix. Alternately, you could have also said H must be an orthogonal matrix. Both will give you essentially the same decomposition. Here, instead of just using orthogonality, we're going to say the rows of H are statistically independent of one another. Right? We're going to impose statistical independence constraints on the decomposition. And that's what we'll cover in the next class. I sort of apologize for this kind of crappy closure to the class. I could have done a better job in the second quarter, but I'm currently not in a mental state of mind to do some math on the board. Any questions? No? Thank you. I'll see you from the next class on Zoom, because until the end of October, we're going to be on Zoom unless you're otherwise notified. Right?